I also appreciated the spread elbows discussion. And I remember in graduate school, which was like a really long time ago, that one of my girlfriends said, I don't get it. I've seen guys get PhDs based on vibrato alone. So I've loved all the talks I've been to. I unfortunately came late because of travel in the Midwest, yes. And, but I also want to say that one of the things that I love about these conferences, and I haven't been to that many, and when I started out there was nothing like this, is the variety. Okay? So what the speakers are recommending, or their experiences, or the physics, it's incredibly broad. And what you guys are going into, whether it's education, research, engineering, applications, whatever it is, astrophysics, biological, what I like about these things is there's a lot more choices than there ever were before, and you're not as afraid to make them. And I want to say one last thing, is that people my age and older, one of the things that's very different about me and you is that no one my age made a decision to go into physics in high school or college. We were all hardwired for it. So it's a different approach. There was no one there to try to convince me, hey, this is a good science class. And so it really is very different. So sometimes I love to give advice, but I would also say that my experiences are very different than yours, and I could tell you about them, but they might not help you out. But they might. And so I guess what I'm going to say is I'm just repeating what a lot of other people said. Stay in contact with a bunch of people, get advice, build your network. If you don't like what your department head is doing, say Laura Green's going to come and talk to you. But we do stick together on this, and it's important, and I'm just really gratified to see this, and I want to thank Kathy and all the other organizers, and it's fun to be home. Anyhow, I'm going to give a science talk because I'm talking to people. That's what I find out people want. I'm going to stick around until about 2. Please feel free. I guess I'm on a panel. I don't know which one. But email me, whatever. We can always be in contact. I think it's really important. Anyhow, I'm going to talk about high-temperature superconductivity. And last year I talked about competing phases and broken symmetries. And I'm sort of going into slightly new areas, but what the main topic is taming serendipity. And we do this both in physics and in life, but we can do the life stuff later. But you'll see why it's taming serendipity in high-temperature superconductivity. And what we have here are 3 major applications for superconductors. One is power transmission, the grid. One is turbines and creating energy. And another one is these are just magnets. It's called SMES, superconducting magnetic energy storage. And I'll show you why they're really an exciting new area to add for our energy reliability. And that's the periodic table of the elements, where we look around, and that's for the mechanisms and how things are paired and Cooper pairing. And that's a picture of my family a year ago. And when I talk about taming serendipity, I have a very large family. My life is I used to call it a semi-controlled crash. I think the semi-control could be taken out of it. But, and when people tell you can and you can't do something, I can't do what I'm doing. It's not possible, but I kind of wriggle my way through, and friends help me, and I help friends, and you kind of do it. And, and like all the other talks said, if you have the passion, you can make it through. So the outline of my talk is as follows. I'll tell you a little bit about what a superconductor is, because talking to some people here, they weren't quite sure, and what, in fact, a high-temperature superconductor is. Why we need new and better superconductors. Why would we need something like that? And then, because this year was the 100th year of the discovery of superconductivity, I was meeting myself in airports. The history is really interesting. The history of the materials design, as well as I decided to put in a little bit about the BCS theory of superconductivity, because both the history of the discovery of materials transformed the way we think about materials physics, and in fact, BCS transformed the way we do theoretical physics. Now, I'm not going to go into a lot of detail. These are just little carrots that if you guys care about, you'll follow yourselves. Renewables, just a second on that. How we could make better materials towards material design. My measurement is point contact spectroscopy, and I had to stick a little bit in here because I just submitted a couple of physics, hopefully. Well, we'll see. So they're on the archive. So conclusions, questions, and I'm happy to talk about anything I have gratefully to say or embarrassingly to say, nothing to hide. So defining properties of a superconductor as are very simply 0 electrical resistance if it's working right, and perfect diamagnetism. And this is due to macroscopic phase coherence. I'll talk about that in a second. So this is resistivity versus temperature, and I'll show you another plot that Kamerlingh Onnes found when he discovered it 100.7 years ago. And the resistance in a typical metal reduces with decreasing temperature, and in a superconductor it drops precipitously to 0. Just to remind you that when the resistance is 0, okay, this is the old analogy. By the way, I like to teach analogies in my senior thesis course. And I'll throw a few analogies in here, and they're very important for understanding things. And if you push them too hard, they fail. And I like to remind people that the Bohr theory of the atom, and I consider Niels Bohr one of the greatest minds of the 20th century. He's up there with Einstein, in my opinion. That Bohr theory of the atom was crucial for our understanding of quantum mechanics and binding and everything like that, and it's completely wrong. So we have to keep that in mind in our analogies. So here's a space heater and a copper wire, and the current goes through the copper wire and the hard coils in the space heater, and the heater gets hot and the coils stay cold because the resistances of those wires are different. So the power dissipation is different. In a superconductor, the resistance is 0. It's a little hard to understand Ohm's law when R equals 0. But in fact, what that means is that if you're transmitting power, if you have a generator here and you want to light up a light in UCLA, you can do it using superconducting wires, and you won't need step-up generators along the way. There is no power loss. So that's one of the interesting things. And all superconductors must be cooled. We believe someday we'll find a room temperature superconductor, but we don't know. Just to remind you that high temperature superconductors, it's still pretty cold in there. And the highest TC up to date is 165 degrees Kelvin. So the conventional metallic superconductors got up to about 30 degrees. And so they needed liquid helium to be cooled. Liquid helium is about 4.2 degrees. Or we do have, in the field now, we do have regular Joule-Thomson type refrigerators that we can cool to these low temperatures. But they're a little more complicated. But right now, the big exciting revolution when the high temperature superconductors were discovered is that they superconducted above the temperature of liquid nitrogen, which is cheaper than, my joke is, beer or milk, depending on who your audience is. Defining properties of a superconductor, the perfect diamagnetism. You've probably seen these or played with it. I didn't want to carry liquid nitrogen on the airplane, so here's a little picture you can get off the web. And has anybody played with this? Yes. Are they like cool? Yes. Okay, so, and I can show you, there's a new one on the web where one of my friends in France put together where it has this track and it hangs. And I just want to add, see how that thing sticks up there and it hangs and you played with this? This is why it's advantageous to use superconductors for magnetically levitated trains, because there's something called Harshaw's theorem, and if you try to balance two magnets together, it's an unstable non-equilibrium case. And it's a little more difficult to do it, but I will say I've been on the maglev in Shanghai, and it is really cool. But it's magnets. It's a different kind of engineering. There's real reasons why you want to use superconductors. The very first levitated train, this technology has been around forever. The very first levitated train, I think, was built in the 70s in Japan, and it was using conventional superconductors, one that I'll mention here. It went for about 1 kilometer, and my Japanese colleagues always told me it went far enough to take their funding agents for a ride. Here's another example of levitation here, and I just like to show this. It levitates because it's diamagnetic. It's for different reasons. Water is diamagnetic. Andre Geim got the Nobel Prize last year in graphene. And he's the only person that ever got 2 Nobel Prizes. One was the Ig, and one was the Physics Nobel Prize. And last night's colloquium that we heard from Professor Gates about playing with things, Andre and Victor, I know these guys in Manchester, every Friday afternoon they just did stuff, right? And taking Scotch tape and peeling off pieces of carbon is what got them the Nobel Prize. And they're really cool people. So now these arise, I just want to throw some of this in, from macroscopic phase coherence, which is broken gauge symmetry. Last year I kind of explained that in more detail. But basically what it means is that the electrons, which we know are waves, condense into a single quantum state. So if this pointer was at this temperature, this metallic pointer on the outside, each electron has e to the ikx minus omega t plus phi as its wave function. And they're kind of unrelated over any kind of a reasonable length scale. What happens when you cool, if this is niobium and I cooled it down to 4.2 degrees below its TC, superconducting transition temperature, the electrons condense into a single condensate. And now, instead of using 10 to the 26 equations to describe this, you need one BCS equation because you have one quantum state. Is that cool or what? Which means if you know what the phase is here, you know what it is here. And that's very important for applications and all kinds of things. But the electrons are fermions. What about Mr. Heisenberg? You can't do that. So you've got to bosonization them. You've got to get these 1/2 to get together and be either 0 or 1 in their spins. How are you going to do that? How do you stick them together? You can't do that. You can't repeal Coulomb's law. Well, that's where BCS comes in. And that was, they figured out a long-range interaction, and the history of this is like really cool. And we had a conference on this on the 50-year anniversary, and there's a lot of stuff on the webpage. I always recommend reading something in history and physics because it helps you get yourself situated where you are. This history is really fantastic. But anyhow, they're bound in something called a Cooper pair. There's an old analogy that breaks down a little too quickly, which is that how do you get them to pair up? Well, if you have two people on a soft mattress, and they're not even attracted to each other, if the mattress is really soft, they'll roll into the center. And that's not because of the person-person interaction. That's because of the mattress interaction, the person-mattress interaction. Okay? And then if it's a really, really soft, squishy mattress, it'll get really deep, right? And then they're really stuck together. And you can really push this a little long. So the strength of the glue that's bringing them together in a superconductor is the energy gap delta. So the larger the gap, the stronger the glue. Let's get a little more real here. Pairing in conventional superconductors, not high TC, is that the pairing interaction comes from something, there's a time delay. They're actually paired in you guys in physics, you should get there really soon. I always talk about chemistry versus physics. Chemists, and I work with chemists all the time, we need to, I'll get to that later on. Chemists live in real space, we live in K-space, okay? They can have their configurational space, momentum, that's where we live. And that's where these guys are paired. And if you're not comfortable with that, we'll talk more, you'll get there, because it actually is something you can get in the belly, paired in this kind of space. Anyhow, the way you can think about it is there's your soft, squishy mattress, and so these are the ions in a niobium. I don't have the crystal structure perfect, but it'll work. And if below the certain transition, at high temperature, of course, you've got phonons beating around, and so there's not a strong electron lattice or electron phonon. Phonons are the normal modes of the lattice. So at high temperature, everything, boiling water, the electrons bounce around, and as the temperature gets lower and lower, the KBT energy becomes less than, in some materials, the electron-phonon, electron lattice interaction. So below TC, this first electron goes running through the lattice, and that's a stronger interaction, and it distorts the lattice. Okay? The mattress gets squished in. Okay? And what happens is that leaves a positive wake, so another electron will go through. This will break down if you push it, and I'm running a conference this summer called M2S 2012, and there's a superconductivity flash mob. And actually, if we have time, and I'm internet at the end, I'll play it for you, but it kind of does this, and so this gives the idea it takes time for the mattress to come up, et cetera, et cetera. So this can work out even if the people are repulsed by each other. You need this time delay. The pairing mechanism in high temperature superconductors remains elusive 26 years later. Don't get upset. Superconductivity was discovered in 1911. BCS was 1957. And these are things like lead. It's not bismuth, calcium, copper oxide with strontium in it, and it's kind of, And so, so I'm just going to add, this is another analogy that some people like and some people don't like, but why does it have no resistance? You've got this big correlated set of electrons, right? Now think about rolling a wheel on a bumpy road. You roll a wheel, and it hits a boulder, and it scatters away. But if you've got this big blanket of guys that are hanging on together, they just kind of skim over those boulders. So I think of it as an SUV with a big wide wheelbase. So you can just sit there and drink your coffee on the road, but not talk on your cell phone. So now, why do we need these new superconductors? We really do. And you know, this whole energy thing, I've been on this commission for the Department of Energy for like 11 years now, and I hear all these stories, and I'm feeling really badly what I'm doing to my children, what we've all done to our children. But so that'll be the applications part. But let me just start out, and that I've switched fields many times in my life, and I got into superconductivity after I got my PhD in far infrared and nonlinear optics. And I thought I switched already. Even as an undergraduate and graduate student, I tried different things. Man, this stuff just really sucks you in. It just gets more complex. The onion skins keep growing. And they're really fascinating. And not only are they playgrounds for broken symmetries, which was last year's talk, but we don't know how to design them. And we don't understand the mechanisms. And what do we do about multiband? There's many Fermi surfaces that, man, they are so complicated. And then you get this idea, oh, I almost have something. Oh, no. And so they're very fun. But I will also say that a lot of my theorist friends have left complex and unconventional superconductors to go to cold atoms because, frankly, it's easier. Okay, so the theoretical, we need breakthroughs. And I think we're getting them now. But we'll talk about that in some detail. And then applications. There are many applications. MRI, high-frequency detectors, cell phone filters, fusion research. But there's limitations on all these things, and better superconductors would be transformative. So here's the fundamental research side, and here's the application side. My postdoc advisor was John Rowell, and this is a planar tunneling. You probably did tunneling in school. So it turns out that tunneling gives you something about electronic structure. This figure right here, okay, this is the derivative of this. This is the conductance. So current voltage, you take a derivative and get the conductance. And then this is basically the density of states from the second derivative, a little more complicated than that. But that curve from tunneling was the mechanism. This curve proved BCS theory, electron-phonon coupling, was what causes conventional metallic superconductors to superconduct. We have nothing like that for the high TC or heavy fermions or organics or whatever. Here's the applications. The ITER project is the one in France that's going to give us all this wonderful energy through confined nuclear fusion. This is just an example of niobium-310 that's used in that. And I'll talk more about those kinds of wires a little bit. OK, this is the big overview. The 20th century, the National Academy of Engineering called the power grid the major triumph of 20th century engineering. Not everyone agrees with that, but it is pretty cool. And you can get these pictures off the web. This isn't the grid. This is actually the Eisenhower highway system. But it does give you where the population centers are. And you could, where's I-74 over here or something? I don't know. But what we do see is that if you're going to get sun power or solar power, wind power, this is where you mine it. And if you want to get geothermal, you get it here. And I'll mention later on, there's also a lot of wind to mine offshore. But if we look and see where the bright lights are in big cities, that's where they are. So one of the problems is that even if we make use of renewables, we still have to transport that renewable energy to the population centers. And one way to do that is the power grid. And one way we can make that better is with superconductors. Clean and sustainable energy carrier, yeah. OK. And let me just tell you how the demand is going on here. If you think you're so cool because your parents got an Energy Star refrigerator, let me show you how much energy we're using here. From 1900 to about now, we're using 40% of US primary energy is devoted to electricity production. OK? Let's get more of this on renewables. Let's not talk politics. Let's not talk about getting oil from offshore. Let's talk about one of the most precious resources on the planet, petroleum. And what do? We burn it to make heat and destroy it, and it's not renewable. It's insane. And on top of that, we can't afford to put another carbon molecule in the atmosphere. Right now, we net, after the oceans soak up whatever they can, 62 gigatons of carbon going into the atmosphere a year. And that number will grow dramatically as the oceans are heating because the ability to take in the carbon drops precipitously with temperature increasing. We don't know what's going to happen. So I think not only should we stop burning our precious resource of oil, which we can use for other things, but we also need to look for energy production and carriers and storage that does not put any carbon into the atmosphere. The grid has particular challenges for the 21st century. The growing demand gives us tremendous bottlenecks when we get into cities. It's already, if you look at this Physics Today articles, if you look under William Street, it looks like a rat's nest of wires because we need to get more power in and out of the cities and we're at capacity. We also have lower reliability. We've lost in the past, I can't remember what this is over. I don't think it's 1 year, but I think overall in the past several years, we've lost $79 billion in the US just due to brownouts and SAG and things like this, which I can tell you about. It's not reliable. And when you have to close down a plant, homes, hospitals, it's a problem. Finally, we need to accommodate renewables, as we're going to add renewables. And the US wants to have 17% of our energy from new renewables by 2020. As we accommodate more renewables, that will put more and more stress on the grid. We don't want to take the renewables, put them in trucks, and drive them cross country. So what do we want to do with superconductors? They will carry energy, generate energy, and store energy. They will carry energy in transmission lines. They will generate energy in wind turbines, and they will store energy in these SMEs, superconducting magnetic energy storage. And I'm just going to go through this quickly. Each one of these could be 6-hour talks. There are 2 generations of high-temperature superconducting wires. Almost everything that's used in ground that's prototyped is this first generation, and they're really lousy. But they're good enough to be reliably in the ground since like 2006. And what these were was a silver sheath with a certain Nabisco, which I'll tell you what, it doesn't matter. It's one of the high temperatures, just kind of packed in there. And they're lousy. I mean, if you take this thing, a wire like this, and you bend a little more than this, it's not going to superconduct anymore. It's not, well, but it's amazing. There's a second generation wire that really knocked my socks off. The second generation is this complicated multi-layer set of wires. Only 2% of the cross-section, this uses the superconductor YBCO, only 2% of the cross-section is superconducting. Yet it still carries 5 times the power that copper does at the same temperature. So that will help the bottleneck. They can make these in rows and rows. There's more and more being used in the field. The problem is it's still expensive. It still needs to be cooled quite a bit. Okay? There are problems with critical current. How do they work in magnetic fields and when you put it high currents? And I think the biggest problem is that they take so long to make. The Korean government has put in for a huge amount of this stuff to be used in Korea from Superpower, one of the companies, and it could take Superpower 3 or 4 years of continuous production to produce the wires that the Korean government wants. So it's really complicated. So those are ways we have to address this to really impact grid penetration. So these are some of the barriers, but I want to move on here because I've already mentioned that. And here's some of the pictures. This is nearby here. This has been in ground since 2006. Unfortunately, this past year, the Department of Energy zeroed out the superconductivity program in the Office of Electricity. So I think these are, you get it? I don't get it. So anyhow, there are some places. This is different in-ground cables, and this is a step-up, step-down transformer station. They're pretty cool. I just want to say that at this point, 52% of our electricity is generated by coal, which accounts for 34% of our CO2 emissions, among other things. So let's not do this, let's do this. Okay? Let's collect energy by solar panels or where superconductivity can have an impact as turbines. This is one, thank you. Well, I think actually I have the coffee because it's warm. I have what everybody else gets this time of year. Well, in good company. So the plan is, and we hope this will work on as we make the superconductors better, to have a parallel grid along with the existing grid that will be DC and buried cables. And so this is a new direction we want to go for superconducting buried cable. An interstate highway system for electricity. And I want to point out one of the reasons this is needed is there's actually 3 power grids. There's the Western Interconnect, which is not connected to the Eastern Interconnect, and neither are connected to the Texas Interconnect. I'm saying it with a straight face, didn't say a word, okay. But there's something called the Tres Amigas project, in which case they're going to bury cable and connect these things. And you have an easier time if you just have two AC sets connected together, they're out of phase, you're going to lose power. So the idea is to convert them down, convert and invert down to DC and back up again and connect the grid, to have a contiguous interstate highway of electricity, seamlessly sending power across the United States. And this is just, you can look this up, there's been a lot of actually Scientific American articles. It turns out that superconducting generators are half the size and weight, and they have a very large capacity. And the idea is to use these things offshore because they are lighter and they're easy to cool. And so this is a picture of, I don't even know where this is. But this is a picture which the idea is if you can set a bunch of these things offshore where you're nearer to the population centers, that's a good thing to do as far as creating energy for the population centers. And this is the SMES. And so this is a technology that's been around for a long time. And how come? It's on and off. So we're working on this with the other superconducting company, Superpower. The other one was American Superconductor. And we're trying to, we have prototypes of these. But the bottom line is this is just a coil. And you can throw energy in and take it out fairly quickly as opposed to switching on and off generators. And here's how you collect energy from a photovoltaic. You have, in the daytime, you're going to have more energy you're going to pick up from a photovoltaic than at night, but they also tend to be very jumpy. And so what you're actually doing is collecting the energy, and you can collect it very jumpy, and then you can pull it out smoothly. And there's several of these in ground in Michigan. And so those are the directions we're going for applications of superconductivity. And here's the perspective. Let's have everything carrying energy around, blah, blah, blah. OK. So I'm part of a group called the Energy Frontier Research Centers. And I just want to say a little bit about this. This was the Obama stimulus package for science. And it was really wonderful. It had tremendous impact. There was a planned $777 million commitment over 5 years, and there's 46 of these Energy Frontier Research Centers spread all over the United States. They came out of books that have come out of the Department of Energy. If you have any interest in this at all, they're all freely downloadable, open access. And so we wrote all these things. The very first one talked about Bob Smalley, who got a Nobel Prize for carbon nanotubes, has a statement in here in the executive summary saying that we need to go after securing our energy future with the same strength that we did in the Manhattan Project before, in World War II. And he was saying that in 2002, and there's more to be said on that. And so these were a bunch of books. There were 10 of them, okay? Besides this one, there's 10 going through here, which is Basic Research Needs in Blank to Secure Our Energy Future. Solid-state lighting, matter-extreme conditions, superconductivity. And then what happened was the hydrogen economy got through, and then pretty much our government stopped supporting this stuff very well. So they didn't have any impact. And then we decided to write this newer one up, which is 5 Grand Challenge, which is this one. But it was too long, and nobody read it. And then so he wrote another one, which is, this one here, I'm sorry. This is great. It's called The New Era, New Science for a Secure and Sustainable Energy Future. This is the one you should download because it's short. Okay, and this is the one that we honestly believe had the impact. It just basically, you know how you study for an exam, you have all these notes, and then you render them, and you render them, you render them until about a paragraph, then a word. That's kind of what we did here, but don't forget the word. And then this last one here has to do with how we can get basic research to work more readily with the marketplace and industry. But that's another story in itself. Anyhow, there's a lot to be done here, and there's a lot of basic research all the way up through applications, regulators, and administration. There's a lot of opportunities here. So we were pretty proud of this 2006 report, right? We are so cool. This is what you have to do. Here's our ubiquitous TC versus time plot. So here's the discovery of superconductivity in mercury, and here's TC moving up, and these are the conventional superconductors. For some reason, it was decided to put little, break this off here, so it really extends down here. I don't know why that was done. But if you notice here, this is the discovery of the high TC, and all these other kinds of superconductors, and now there's more, it kind of fractals off, right? And the only ones we really understand are these. Okay? And so the other thing that came out of this report was a ubiquitous phase diagram. And here's one example of it where you've got a dome in the center, and you've got over here, this is a standard metal, which we call a Fermi liquid. And over here, we've got strange stuff, okay, which we don't understand. And the strange stuff is different for all these different kinds of superconductors. And we are, in the cuprates, the high temperature cuprate superconductors, this is what pseudo-gap, blah, 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 you know, Martinez, blah, blah, you know, and so there's still a lot of research in there. And I'll talk about why this is important, but we all understood that if you have a quantum phase transition, this is important. I'll say more about this in a minute, but basically what we have here is a thermodynamic phase transition. On this side, there's one kind of phase, and on this side, there's another kind of phase. If you're going up and down in temperature, that's a thermodynamic phase transition. Boiling water, freezing ice, right? If you go across this direction is pressure or doping, electron concentration, okay? So if you're going along this way with pressure and you go through a phase transition, it's not thermodynamic because it's not temperature dependent. That's a quantum phase transition. Now, how do you go from here to here and have the thing not blow up in your face? You create another phase that protects that quantum phase transition. And this kind of picture here, this dome in the center, strange stuff here and strange stuff here, is the poster child for quantum phase transitions. And so we said, okay, we're going to do this. We're going to design new superconductors. We're going to take, these are strongly correlated materials here. By strongly correlated, we're meaning that those electrons interact with each other, and we can't predict it. No one predicted superconductivity. No one predicted heavy fermions. And it has to do, there's other kinds of instabilities like a Pomeranchuk instability, or reasons why electrons will correlate. And it's not due to the underlying lattice. Okay? That's a wide open area of study. And so how we're going to design things that we can pressure tune, and if we're lucky, the emergent phase will be a superconductor. And the one thing that we're sure of is the stronger correlated you make that phase, the higher temperature this emergent phase comes. So, okay, you give us some money, we'll figure it out. Okay, we're going to do it. So what happened? We didn't figure it out. Nothing happened until come along Hide Hisano, and much to our surprise, he discovers a whole new class of high-temperature superconductors. Here's a guy looking for, I mean, actually, he's really proud of this. One of his materials is going to be in the iPad 4, or the iPad, whatever the next one, iPad 3, the next one coming up. He's a chemist, University of Tokyo, studying transparent conductors, and he found this. Okay, transformed the whole field. He wasn't looking for it. I want to say that this is a serendipitous discovery. So our center, this is what we're doing. We want to make better superconductors. And sorry, I should say more. So it's between Brookhaven, Argonne, and University of Illinois. These are directors. I'm one of the subdirectors. And what's really nice is besides the basic research, we interact very, very strongly with American Superconductor and Superpower. And it's not that American Superconductor says, you need to measure this for me, and we say, you need to give us this. We say, what are our grand challenges? What do we want to figure out together? And when we have meetings and evo calls and everything, that's the way it goes. It's not that, what can you do for me? What can I do for you? What are the grand challenges? And that's what that SciTech report is about, what I mentioned. So let's go on. I have to say a little bit about the history here. And this was serendipitous. I strongly recommend this article in Physics Today. And here's Kamerlingh-Onnes' plot here. Kamerlingh-Onnes, the race for the cold, okay? He just wanted to learn how to liquefy helium. And he won. He figured it out. And serendipitously, he said, wow, mercury is liquid at room temperature. It's clean. What will happen if we cool it down? And Lord Kelvin said, you'll freeze out the whatever conducts. Matheson said it'll go flat. Dewar said the resistance will go to 0. Nobody predicted that. Nobody. Couldn't have predicted it. No way to predict it. I also want to say that I have a press release in 1920 in Chicago where he said that superconductivity was going to solve the world energy crisis. Man before his time. The history of materials were really sweet. Basically, people just kind of measured materials to see if they were superconductors. And then Bird Matias discovered the first new class of superconductors. He started combining things. He took a magnetic and a semiconducting material and mixed them and came up with the first new kind of superconductor, cobalt silicide. And I'll mention Mathis's rules in a second, but his rules were great, and he really set the stage, but it didn't help us in the high TC superconductors because they were a completely different class. I want to stress that part of my research is not just making newer, higher temperature superconductors, but making them hold currents better. And I just want to say just one or two slides on that. John Hume, about the same time, working with his graduate student, discovered the first of something called an A15 superconductor. It's this kind of cute little structure. It's like interpenetrating lattices, okay, where B is a transition metal. There's dozens of them. And the highest goes up to about 18. Actually, I just realized in thin film, I just wrote another paper on this. This is an aged slide. People have pushed this up to 23.3 degrees. So this has gone 23.3 degrees for niobium through germanium. These were the first materials to actually be able to carry superconductivity in a reasonably sized magnetic field. And why is that important? Applications. If you're going to make MRI or the ITER project or whatever, you better be able to carry current in a field. And that's why these were important. And when my boss, Jack Wernick, retired from Bell Labs, my boss, John Rao, said, high TC gets Nobel Prizes, high JC. Jack invented a lot of the A15, saves lives. I thought that was really sweet. So that's very, very important. Now, looking away from the applications, more of the history, Frank Steglish discovered the heavy fermion materials. These are materials which have 4F or 5F atoms in them in a lattice, and it all has to do with the Kondo effect, and it's gorgeous stuff to study. The electrons are very, very strongly correlated. And in fact, at low temperature, I've been studying these since the early 80s. At low temperature, the mass that you measure thermodynamically from specific heat becomes extremely large because there's a strong magnetic scattering and the strong correlation across the system. Not superconductivity, another kind of strong correlation. M stars get as high as 1,000. Okay, really cool. And it's not due, if you've had solid state physics, you know, if you know the band structure, the curvature of that band structure gives you the mass of the effective mass of the electron. This can't be explained that way. It's really interesting stuff. I also want to say that this is the first time we ever really understood that dome. These were the first really tunable superconductors, and all these materials, if they had a lot of magnetism in it, had higher TC. So all of a sudden, magnetism looked good for superconductivity, when magnetism always killed superconductors before. And so at that point, BCS started to fail. The electron-phonon interaction for BCS started to fail. That led to something, I've worked on this material, these 115s, cerium, cobalt, indium-5. These materials were discovered not only by serendipity. The people that worked on these materials looked at the strongly magnetic heavy fermions and the superconducting ones and found a way to combine them and push the TC up. So that's pretty interesting. Now they have to just repeat it. Now the oxides. 1964, Marvin Cohn predicted that strontium titanate would superconduct, and it did. I don't know how he did it. I still don't understand that paper. I've read it 100 times. He's a brilliant man. Another great story is that Len Mathis and Don Hammond calculated this material. They did the electronic structure calculation on that, and then high TC was discovered. And they went back and they go, strong correlations. And they went and predicted that if we made this material, it should be a higher TC. And Len Mathis, who's a theorist, you know, was down the street from me. I had already moved to Belcourt, actually went into the lab and made the material, right? And he did a lousy job, and then Bob Cava, who's a genius at the solid state chemistry, pushed this TC up to 30 degrees. Amazing stuff. And then there's a high TC, 1986, Bednorz and Mueller discovered lanthanum, barium, copper oxide, and then Wu and Chu, through other kinds of substitution push us up to 90 degrees. The highest TC now is about this temperature, 165 under pressure with this string of elements together. It's not practical. Going from the copper age to the iron-based superconductors, it was amazing how fast this happened. After Hasano's discovery, Professor Zhao in China just They doped I know these guys. They're good scientists, and they work hard, and they're very smart, and they did a whole bunch of doping, and they pushed it up from 26 to, it's actually 58 degrees right now. And to me, why this was a shot in the arm to the field is we now know there's two kinds of superconductors. Let me step back again. For something like 22 years, the only high TC superconductors were the cuprates. Okay? For the first time, a totally new class of superconductor proved to be high TC. We like to say the iron-based superconductors broke the tyranny of the cuprates. And the logical step is, if there's two kinds, there must be a third. Let's go out and find it. And that was a shot in the arm for the funding, yes sirree. So George Crabtree put this together, and it's a really nice, he kind of listed 10 different families of superconductors. These are 10 distinct families of superconductors. There are more than this. And there are many, many, many different kinds of superconductors within these within these different families, many kinds of cuprates. So there's hundreds and hundreds and hundreds of superconductors. Almost every single one was discovered serendipitously. We don't know how to design them. I like to throw this up here, Paul Canfield's vision of the periodic table. This is where you go to study them. Hydrogen, a little less than hydrogen, less and less like hydrogen, hard metals, copper, gold and silver, silver, gold, semiconductors, stuff that might not be real, won't be on the final exam, bombs and other nasty stuff. I spend a lot of my time down here, okay? I spend a lot of time in lanthanum and cerium and uranium because they make really, really cool superconductors, okay? But, so this is something that I think is probably a girl thing, but Rick Green, I've been working with him, we're not related, okay, at all. But when I was younger, we'd go to these conferences and I'd go, hey, Dad, you know, he'd get all embarrassed, you know, and then people got over it. But it's the Jewish green. So the green with the E at the end is either Irish or Jewish. And none of the Jewish greens are related because we all changed our name from something else. My father came to this country as a Grossklick, you know. So we're all unrelated. Anyhow, just like superconductors. So this is an international institute that people buy into. And I've been holding some sessions. I'm going to be holding meetings where this is our charge. Because of the need, there is a strong support in the US and internationally to find new classes of better superconductors for our energy challenge. For any one of us, putting all of our efforts into total serendipitous discovery is frankly nuts, right? I'm given money to do superconductivity research. Am I going to put all my effort in making new superconductors? Or am I going to make electronic structure measurements and get papers published, right? I mean, this is just too hard. We are therefore sharing our expertise and resources on a worldwide scale. This is a paper, an article I wrote for Physics World. And I just want to point out why one of the reasons this is working, and we are sharing, let's all share, world peace, is that my very first meeting, one of my colleagues at a different institution said, well, why would I share any of my great ideas with you? And one of my other colleagues said, you know, if you had such good ideas, you wouldn't be here. You'd be home in the lab doing it. So we don't know. And what's come out of this, actually, is a lot of really novel ways to go after this. They may all fail, okay? But we're doing it. And it's really exciting. And there's a paper that's in production right now, which actually has done some real prediction using a new kind of calculation. Anybody hear of DFT? Okay. Anyhow, so DMFT, DFT plus U. There's these new modes of calculation that are helping us to predict in these strongly correlated systems. And it's really fun. So what are we doing here? This is, when I have longer seminars, I go into exactly why. But these are our Matheson's rules. Okay? These are what we're looking for that help create these competing phases. And the strong competing phase will give us a strong emergent phase. Reduce 2D is good. Transition metals are good. Light atoms seem to be good. And I can give you all the reasons why. They're tunable. There's ionic bonding and a low dielectric constant. Anybody want to discuss why these are important? It's not, now what's happened is we put these, you know, we did the bookkeeping and found the higher TC materials all have this. And now we're starting to understand why. And now we're trying to design these materials. But the whole point is to make a higher temperature superconductor. How much time do I have? How much time do I have? 10 minutes.
Well, how many questions do you want to take at the end?
OK, so what if I take 3 or 4 more minutes? Is that good? OK. So here's that phase diagram. Everybody has it. That's the one that everybody quotes. And these are just other materials. They all got the domes. They all got competing phases. OK? Everybody's got this. You know, everybody's got it. And so this is what I'm going to talk about right now, because I have to. So what we knew about this particular iron-based superconductor was that it had a weakly correlated antiferromagnetic on this side, a simple Fermi liquid like gold type stuff on this side, and there's the dome. Where's the strong correlations? Well, we found them, and that's what we just submitted. This whole area of the phase diagram, we found that on the lower dope side on this phase diagram, this pink slashed area, those that just got up there, is what was measured for strong correlations. And I won't have time to tell you the whole technique, but this is a technique that has been around since the 70s, and we've been able to develop it to not just measure superconductors, but to measure electron scattering in the normal state, and it specifically picks up strong electron correlations. It's called point contact spectroscopy, where you put a very sharp tip and you touch it to the sample, or there's other ways we can do it. And what you study is quasi-particle scattering into the material. So you scatter an electron into the material. Let's just look here, because if it's too dirty, you don't get anything. And if the electron scatters out, and it's a really small aperture, this isn't resistivity. This isn't a big aperture where the electrons scatter through and you measure resistance, OK? This is you're measuring through a little tiny aperture, and if the electron scatters bad, you can measure that in the conductance measurements. And we've done the analysis and blah, 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 and that's what we found. And oh, I went in the wrong direction. I'm sorry. OK, so, oh, no, I know, I didn't go the wrong direction. So what I want to do is show you that all these dots here are where we measured these materials. And without going to detail, this is the parent compound, which is not a superconductor, and we get this interesting shape of conductance as we lower the temperature. And as we go across the phase diagram, we still see that. And at the other side, we don't see it. So the bottom line is, with a lot of analysis, we were able to show that this is due to an electron nematicity. So what happens is the electrons break the symmetry of the underlying lattice. At that high temperature, above that transition here, up here, okay, this material in this whole white area here is tetragonal. So it's C4 symmetry, okay, C4 symmetry, and it's non-magnetic. And what we've shown is we break that C4 symmetry. That's what electron nematicity is. Just like a nematic liquid crystal. That's a picture of a nematic liquid crystal. So some kind of electron correlation occurs that doesn't match the underlying symmetry of the lattice. If it doesn't match the lattice, that's the definition of strong electron correlations. So that's what we've been studying. And my conclusions is, let's work together and find new superconductors. Let's understand why they superconduct. And let's learn how to design materials. And I thank you for your time. I do. Thank you for asking that. Actually, what you have to find is some place you overlap. So I've been working for chemists for ages. So when we were making the old high TC stuff a long time ago, I actually sat down and learned a whole lot of chemistry so I could understand bonding, and I went there. And then once you have some place that you understand, you can build from that. I did this whole other project with the chemists at University of Illinois, and I knew that we could work together. And I'd go with my graduate students to his office. He had his graduate students, and it was like this. We didn't have any overlap. Integral was measure 0. And the students would start laughing until at one conversation, it takes time. At one conversation, we both, symmetry breaking, symmetries, underlying symmetries. We both realized we had that much in common. And as a result, this thing grew into a collaboration that really was phenomenal. We just had one place to work. We found one place where the language was the same, and we could grow out from there. I have another one, which is kind of a funny story, which I had a collaboration with a girlfriend. We had kids at the same time. She's a biologist. I'm a physicist. And I think because we had overlap that wasn't even physics, we somehow understood each other. And we would talk to each other. She would communicate to her chemist, and I would communicate to the guy who was a nano fab person. And we all got this work done. So I think you have to just spend time together. Hans Fraunfelder was at my university for many years, one of the daddies of biological physics. And what he did was every day have lunch with the biologists. So you don't have to talk about physics. Don't shove it down their throat. You'll find where the overlap is, because we all have some overlap somewhere. Right? World peace? Okay. So you can try it. Like whether it's a sport or, as it was said this morning, cooking, or or another area of science, or it could be astrophysics to talk about new superconductors. That also helps. It doesn't matter. Just some common language. Am I allowed to ask her? Okay.
Yeah, I feel like this, especially what you are doing your research, really borders with nano industry. So do you work in nanoscale?
Yeah. So what's very interesting is a lot of the stuff that I measure. For instance, one of the things we discovered that at the surface of these unconventional superconductors, there's something called Andreev bound states. And those exist on the nanoscale. So except for making the tips and a little bit of fabrication, most of what I study is spontaneously nanoscale. So like pneumaticity, like Andreev bound states. So I would say that I fall into the nano stuff a lot, but what I'm more interested in, somehow I never got into this making little nano things and measuring them. I just never could do that. I like things that are naturally happening. But now a new direction, I'm on a new study with the DOE right now. They're going back to meso, and I go, what is this? That's old. Well, it's not going down to meso. What's interesting now is taking things at the nanoscale, and can we build them up into a controllable mesoscale? And so I think that's the direction that I'm going. But yeah, I do interact with nano guys all the time, and But I will say that strongly correlated electrons, which I work in, really is somewhat different than nano, and it's very interesting when they combine. And so we've done some of that too. Thank you. Good question. Exactly. So in the case of transmission lines, what I mentioned in one of those pictures, we're not going to go rip down all of our, there was a decision we're going to be AC or DC in our transmission lines, okay? We're not going to rip all those down and start over. But parallel to that, parallel to the existing network that we have of the grid, we're going to build underground, buried cable where you could run the liquid nitrogen and keep them cold. And in the cases like the cell phone tower, and by the way, in MRI, they use liquid helium in the MRI because they're lower TC materials. As far as like in cell phone towers, there's in a lot of things, they have to keep things cold. And when they're localized, they don't need to use cryogens. You can do this all with plug-in refrigerators. Plug-in refrigerators will go to millikelvin temperatures now. Pretty interesting. It's a whole neat thing I could tell you about if you want. But, so yeah, you do have to keep it cold at all times.
Can I ask you another question on that one? No, I need to go.
Aww.
It is almost lunchtime, and I think everyone wants to eat, right? Everyone's hungry.
You mentioned that the property of high TC superconductivity is not, the theory under it is not known yet. But you also mentioned that there's some theories that could really predict some kind of high C
Okay, so they haven't, the question was, if I got it right, was I stated that the exact mechanism for the gluing of the pairing of the electrons is not known for the high temperature superconductors. Yet there's been some predictions. Okay, let me just back off if I spoke too strongly. The predictions were to how some materials would react, what would happen to them. And it wasn't predicted what the TC would be, but these calculations were predicting that you could predict certain kinds of electron correlations. Okay, so it was predicted that you have this material, and if you put it under certain pressure, these calculations said that you would go into this other kind of phase transition, and that's what they found. They have not been able to predict superconductivity yet, but that's one of the first times they were able to predict a strongly correlated phase transition. So we're a long way off, but we're going to get there, I promise.